Today we look at the numerical integration techniques using the method of Riemann sum and the midpoint method. These are the simpler methods of numerical integration. So as you can see, I'll focus on the leftmost graph here. If you want to integrate the function which is shown by the black curve, if you want to integrate it, what you need to essentially do is calculate the area underneath this curve, and the way you can do that is you can define some strips, right? First you need to divide this into certain number of subintervals. The number of subintervals here is 3, and then I need to calculate the area that is formed by the strips, right? These 3 strips in the interval. So this is fine. This if for example if I call this x1, x2, x3, x4, then this one will be f of x1, f of x2, f of x3 and f of x4. So I have the heights of each of these with me. In order to calculate the area, I need the height and I need the base. So the base is x2 minus x1, which is delta x. It is same in all the 3. So I have the base. But then you would wonder, what height should I use, because this is not a rectangle, right? There is a curve in between these 2 heights. So what should we use as a height? Because in order to calculate the area, we need to sum up the area of these 3 smaller strips, right? These 3 strips, and they are not exactly rectangles, so we can approximate them to be a rectangle. And the way we do that is, I can either choose f of x1 to be the height of this rectangle, or I can choose f of x2 to be the height. When I choose f of x1 to be the height of this rectangle, right, if I choose this to be the height, right, then again I choose this to be the height, and for this strip I choose this to be the height. If I do this method is called the left Riemann sum, because I am making use of the function value at the left side of the subinterval, right? I have chosen this as my height for this subinterval, this as my height, f of x2 as my height for the second subinterval, and f of x3 as my height for the third subinterval. So that is why this is called the left Riemann sum. Similarly, now I think you have got the drift. So now if I have to choose the right height, so if I, instead of choosing the left height for the first subinterval, if I choose the right height, the height on the right hand side, then how would it look like? So now I'll approximate the area to be given by, this. Okay, let me just use a pencil to draw it. Okay, for this one, for the second subinterval, I'll choose the height to be given by the right side of the function, right side of the subinterval, and similarly for the third one, I'll choose it to be given by the right side of the subinterval. So now that I've chosen the height as the right side of my subinterval, this is called the right Riemann sum. So once I've chosen left, in one method I chose left as my height, in the second method I have chosen the right value of the right value in the subinterval as my height. If I chose the mid value, then that would be a midpoint method of calculating the integration. And the way I do that is, I take the first subinterval. Here I am not going to choose the left as my height, neither am I going to choose the right as my height. What I'll do is, I'll calculate first a value in between x1 and x2, right, and then I will calculate the value of the function in the middle, and that is going to be my height for the first subinterval. So the rectangle which I'll be evaluating will be this. The rectangle which I'll be evaluating will be this one, right? So when I do that, this will be my area and that will be my midpoint method. So it's very simple actually. What you're doing is dividing the interval into subintervals, and then you are calculating the area of the strips formed by each of the subintervals, but you approximate the area, you approximate the strip to be a rectangle, and once you have a rectangle you need to figure out its height, because the base is fixed, it's delta x in all the three cases. So in the first one the height is chosen as the left side of the subinterval, in the second case the height is chosen as the right side of the subinterval, and in the third case the height is chosen as the center of the subinterval, the function's value at the center of the subinterval. Okay, so this is, as I told you, and you would agree that this is quite simple method as compared to the first two that we studied, trapezoid and the Simpson's method. So now we are going to write a code. What we'll do is write a function itself. So let me open up an editor, Vim. You can edit this code in the Octave default editor. I'm using Vim, but both are same. You can even edit your code in Notepad, Notepad++. Right. So let me name it. I'll name the function. Let's call it integral sum. You can name it anything you want. Integral sum.m. All right. So let's define the function. It returns the value of the integration. What was the name again? Integral sum. Okay. Integral sum. It will take in the function value, the left and the right interval, and what else? Yeah, the number of divisions, the number of subintervals. Okay. So let me first write for the right Riemann sum or left Riemann sum. Let me just check if it is recording. Yeah. Left Riemann sum. So I wrote a comment, right? I can write a comment when I give a percentage symbol. So let's start. What do we do here? Left Riemann sum. So first we need to generate all the x values, x1 to x4. So for that we need the value of dx. So dx is b minus a. In fact this, okay, let me write it first. Right. This is going to be common for all the three methods that I'm going to use in this function. So I'm going to copy this here itself. Okay, let me get rid of this. Okay. Right. Since it's going to be common, I have put it outside the comment. So left Riemann sum. What do? We need the value of the function at the left of each subinterval. So we need the value of the function at x1, x2, x3, but not at x4. So what do? Let's generate the value of the function. Or I can simply, eventually what do we have to do? We have to calculate the sum. So I will be what? It will be equal to the sum of the area of the triangles. The area of the triangle is dx times the value of the functions. The value of the functions wherein the x value goes from 1 to 3. So if there are three subintervals, one subinterval, the second subinterval, third subinterval, we'll have 4 x values, right? But for the left Riemann sum, my x values will vary from 1 to 3, or 1 till the number of subintervals, right? 3 subintervals, x1, x2, x3. So I write 1, x goes from 1 to n. And I guess this should give me the value for the left Riemann sum. What is the right Riemann sum? I think you will guess that as well. I is equal to sum dx times f of x of. Now in the right Riemann sum, I take the values of, in each of the subinterval the height value is taken as on the right side. So for this first subinterval, the height is here. Let me write it so that it's even more clear. Okay, so for some reason my tablet isn't working. It was working right now. Let me just try it once more. Okay, it's not. It is it? Yeah, it's working now. So let me get rid of these lines which I drew by mistake. Okay, so this is x1, x2, x3, x4. Right, so in the right Riemann sum, for the first subinterval, we will be taking the value of the height as the function's value at x2, right, f of x2. And then for the second one, the function's value at x3. And for the third one, the function's value at x4. So we are not going to be using the function's value at x1. So since we have 3 subintervals, we'll have 4 x points, and we'll be evaluating the function at x2, x3 and x4. So 3 subintervals, x goes from 2 to 4, so x will go from 2 to 4, and 4 is for 3 subintervals I have x going till 4. For n subintervals I'll have x going till n plus 1. Right, so that's the right Riemann sum. The midpoint method is again simple enough. So what we do is, for each of the subintervals we calculate the function's value at the center. So for the first one, for this one, where is my pen? Yeah, it's x1, x2. So the first one, let's say this is c. So for each subinterval I need to calculate the center location. So what we do is, let's calculate c. Okay, so I would need, let me think how I can do it in a vectorized way. So x2 minus x1, then x3 minus x2. Okay, so I need an array of the midpoints, and how do I, so for the first one, what would it be? x2 minus x1 divided by 2, right? So x2 minus x1 divided by 2. Okay, I don't have to actually worry about that, because I know x2 minus x1 is dx in all the cases. So and dx is already calculated, so it's simple enough. So it's dx, right? So dx by 2. Alright, so we need the function's value at the center. So what do we do? Let me create an array of the center values first. Fine. So the way I do that is, the first center point would be at x1 plus dx by 2, right? x1 plus dx by 2, and then it will vary with an interval of dx until it reaches the last one, which will be here, which will be, so for this is, I can follow my words carefully. The last center point would be here, right? That would be x3 plus dx by 2. So I'll write that as x3. So 3 is the number of subintervals. So xn. So x1. What was x1? If you remember, it was nothing but a, right? X1 is a. X1 is a. And what is x3? X3 is, or I can write it as x4 minus dx, right? Because this is x4 and x4 is b in our case. I'm specifying a and b. So x4 is b minus dx. So I can write this as b minus dx. Okay. So this makes sense, right? If it does, then let's calculate the value at all these points. Dx times f of c, because c has all the values of the midpoints, right? It's an array and I can calculate it here. So this is a bit different way of specifying it than I did in the previous two methods, but anyway this should work. Okay, one more thing I should have mentioned, because I'm implementing 3 types of integration here, I should also specify the type of integration. So let me write type or method, right? Method, or okay, let me write type itself, because I'm not sure if type is a keyword or not. Let me check, because if it is a keyword in Octave, I can't use its name as a variable. So it is in fact a keyword, I cannot use type, right? So in MATLAB you can only use names as variables which are not already defined in MATLAB. Type is already defined, so I cannot use that as a variable name. Okay, edit, not Vim. I cannot open an editor here. Okay, so let me what I do is type I, okay, type of integral. So anyway, so let me, what I do is, depending upon the type given by the user, I am going to calculate one of these things. So for or let me write if type I, how do I to compare two strings? So the user will provide some input, right? So if the user provides left, I'm going to use left sum. So how do I compare the input provided by user to my string value? So the way I do that is, there's a thing called stir compare, string compare, in which I compare the input given by the user with what I have. So if the user types in left, let me write it small. If the user types in left, then this line will be evaluated. Okay, if it types in right, then the following line will be evaluated, and if he or she types in mid, then the following lines will be evaluated. Else, if it is none of these types, then I can print a message, invalid integration. Okay, you can come up with a better name, a better message. I cannot think of any better right now. Okay, so I think this should work. Let me end this with a semicolon so the data is not printed. Okay, fine. So let me take a function, simple function, anonymous function, x square f. So again, let me use our the one defined by MATLAB or Octave. The function defined by Octave to calculate the integration is integral. I need to define the limits. So from 1 to 10, so 333. Let's see how our function does. f1, 10, 100 subintervals, and the type is left. Okay. So the mistake that I've done is a syntax error. Let's get back and correct it. Edit integral sum. So else, it's actually else if, because there is a condition again. Okay, now it should work. Now x is undefined. Line number 6. Is x undefined? Yes, it is. So what is x? X is all the values between a and b. Now x is defined. So does it work? It does. So right. So define a function, and the output by MATLAB is 333. The output by the left Riemann sum is 328. with 100 subintervals. Let's check for the right one. 337, it's not that close. Let's check for the mid. 324. So none of the values are really close, but again, maybe we can increase the number of subintervals. Let's make it 10,000. So this is quite close now. 332.91. Let's see for this 10,000. 333. This is even closer. And for the left, with 10,000 subintervals, 333.96. So these are quite close if you increase the number of subintervals, right? And if you enter some other type undefined, it says invalid integration type, right? I should have printed that out in the next line. So let me just change one small thing and then we'll end. I have to insert a new line at the end of this message. So if I type it now, it says invalid integration type. So I hope it was fun writing this simple simple function which includes 3 different types of integration, and they are quite simple. So thank you for watching, and I'll see you in the next one.